So we can try code it up from what we had before. So let's say we copy this DDT FV and just name it DDT shallow water. Okay. So my n is no longer equal to the length of W because my solution actually contains two variables, my rho, my H and HU. So we have to divide by 2, right? Okay. And my dx, well, for shallow water, it's a little bit more interesting to have a non-periodic periodic domain because, well, at the two ends, we can see reflections. So let's make the domain length equal to 1 instead of 2 pi, and we'll figure out how to do boundary conditions. So let's actually do a reshape to make it n by 2, okay? And then all this is still correct. We will just put a second dimension over here. Well, I don't think I need this dw dx anymore because I have dw dx left and right. Okay, so I have my left and right states. I apply the limiter. Let me just make sure the limiter also would actually work. Okay, and I set the interfaces. Now, instead of the Goodenough scheme, I have to use a approximate Riemann solver, right? So we'll comment out this Goodenough scheme. I think because the way I think I should instead of the semicolon, I think I need a comma, right? So because I'm now, wait, actually it is still semicolon. This is correct. Yeah, sorry. Okay, so instead of a Goodenough scheme, I need to perform the approximate Riemann solver. So first of all, I want to compute the value of the flux on the left and right state. So FPL is equal to now it's time to go to the form of the flux. Okay, so first of all, it's equal to also an n by 2 array, right? So n by 2 array. So I'm going to be separating them. The first is WPL 2, right? So this is the second variable, which is HU, okay? And the second flux for the second equation is WPL so let me instead of this, let me just compute UL is equal to WPL divided by WPL1. So this is HU divided by H. So now the second one can be computed by H times U square, so which is actually WPL2 times U again, L, and plus G over 2. Okay, so I need a G here, so let's set G equal to 9.8 times the square of H, right? So this is my flux function. On the right, I'm going to have the same flux function evaluated on the right state. All right. Yeah, anything I'm doing wrong, please tell me. So next ingredient is I need to compute rather than just averaging them, I also need my wave speed, right? So for the wave speed, I need the absolute value of velocity plus square root of gh. So my wave speed left is going to be the absolute value of u left plus square root of g times my left state taking the first value, which is h. Okay, my right is the same, and we can just take the wave speed to the maximum of w speed left and w speed right. So this is to make sure we have sufficient numerical dissipation. Okay, and then my FR is going to be FPL plus FPR divided by 2 plus dx over 2 times wave speed times w right minus w left minus w right. So that's a WPL minus WPR. So that's my flux. All right, everything else should be the same. Okay, so let's actually remove this impossibility condition, because this is no longer going to be the case for system of conservation laws. So the total variation diminishing condition only should work for a scalar conservation law, because for system of conservation law, even the analytical solution wouldn't satisfy that property. Okay, so now let's actually make a, oh, yes? I need to, line 14 UL. Are you saying this line 14?
Yeah, we need to make it equivalent to UR.
Oh yeah, thank you. Yeah, that's right. Otherwise, we don't have UR as an ingredient for the calculation. Thank you. Okay, good. Yes. So now let's make a, so this is still periodic, right? This is still a periodic solution. So let's actually, in order to make it non-periodic, what we have to do is we have modify the flux on the left for the very first cell. So the flux on the left is going to be for the very first cell. So there should be no mass flux, right? If we have a solid wall, and the momentum flux should be g over 2 times so we actually shouldn't use the information across the domain, so let's just set it to be, yeah, actually I think my extrapolation is also, it shouldn't also use the information across the domain, but let's see if this works. So we should use the solution of W1 square. So this is the basically the H on the very first cell. So FR of end should also be the same, except for it's the very last cell, right? So that imposes the boundary condition for the finite volume, where there is nothing going over the end of the domain. All right. Okay. So another modification I think is I need to make dw dxl on the first cell to be 0, because I shouldn't use the information across the domain. dw drr and is equal to 0. All right.